Good morning, students. Today we are going to see a very interesting topic, that is green chemistry. Green chemistry is the need of the hour and it is also of global concern. First of all, let us see what is the need of green chemistry. Chemistry has improved our quality of life and made thousands of products possible. For example, drugs, cosmetics, dyes, paints, agrochemicals like fertilizers, insecticides, herbicides, etc. Unfortunately, this achievement has come at a price. Our collective human health and global environment is threatened. Our bodies are contaminated with large number of synthetic industrial chemicals. Some are toxic, some are carcinogenic, while others remain unaffected. How does it happen? Chemically contaminated food, air, water, and dust. Even the developing fetus is directly exposed to chemicals in the womb. Many chemicals enter the food chain. Example, pesticides, flame retardants used in furniture and electronics are commonly found in marine mammals. These days, the cancer rate rises. Link between certain chemicals and birth defects and learning disabilities have been observed. So, should we stop industrialization, urbanization, and stop increasing the rate of agriculture production? Yes or no? We cannot afford to say no. So, the key challenge is to combine technology with environmental safety. What is green chemistry? It is basically an approach to prevent pollution. When you look at the definition, we can see that the definition is an approach to design, manufacture, and use of chemical products to intentionally reduce or eliminate chemical hazards. What is the goal of green chemistry? To create better, safer chemicals, choosing the safest and most efficient ways to synthesize them and reduce waste. And now let us see the synonyms of green chemistry. They are clean chemistry, atom chemistry, safe chemistry, eco-friendly, benign by design. How is it different? Traditional chemistry refers to management of hazard. Chemicals are typically created with the exception that hazards can somehow be managed or controlled by establishing safe concentrations and exposure limits. Green chemistry aims to eliminate the hazards right at the design stage. This practice benefits our health environment throughout the globe. Now let us see some of the benefits of green chemistry. Some of the benefits include lesser waste, economical, energy efficient, fewer accidents, safer products, healthier workplaces and communities, protects human health and environment. Dr. Paul Anastas and Dr. John Warner outlined 12 principles on which this is based. So, in order to conclude the introduction, let us see that green chemistry is all about reducing waste, materials, hazard, risk, energy, and cost. Now, we are coming to the important topic, that is principles of green chemistry. Green chemistry is based on 12 principles, and these principles were designed by Dr. Paul Anastas and Warner. Now, in this picture, we can see the Paul Anastas, who is the father of green chemistry. These are the 12 principles, and all the 12 principles can be seen in a single slide here. Now, let us see these principles one by one. The first one is, it is better to prevent waste than to treat or clean up waste after it is formed. Now, what is waste? Unreacted material is called waste. It may be hazardous or may not be. Now, the basic principle here is prevention is better than cure. So, waste which is discharged into the atmosphere, sea, or land causes not only pollution but requires expenditure for cleaning up or treatment. This adds to the overall cost of production. Then, what is the solution? We have to plan the synthesis so the formation of waste is minimum or absent. Now, let us see the second principle. Synthetic materials should be designed to maximize the incorporation of all the reactants into the final products. In short, it is also called as atom economy, which is very important even in the examination point of view. This concept of atom economy was first published in 1991 by Barry Trost, a scientist from Stanford University. What is atom economy? Generally, it is believed that in a particular reaction, if the yield is 90%, the reaction is considered to be good. In that case, the formula is applicable. Percentage yield is equal to actual yield of the product by theoretical yield of the product into 100%. The above calculation implies that if 1 mole of starting material produces 1 mole of the product, the yield is 100%. However, such a synthesis may generate significant amount of waste or byproducts, which is not visible in the above calculation. Such a synthesis, even though is 100%, is not considered to be a green synthesis. A reaction is considered to be green if there are more number of atoms or starting materials incorporated into the final product. One should take into account the percentage of atom utilization. Percentage of atom utilization is equal to molecular weight of the desired product by molecular weight of the desired product plus molecular weight of byproducts into 100. And there is also another formula, similar formula. Percentage of atom economy is equal to formula weight of atoms utilized by formula weight of reactants used in the reaction into 100. In other words, atom economy is a measure of the efficiency of a reaction. Now let us see rearrangement reactions. This is an example. Conversion of allyl phenyl ether at 200 degrees to ortho-allyl phenol. When you look at the formula, all the atoms of the reactants are incorporated into the final product. We don't see any addition of atoms or deletion of atoms. So this is 100% atom economical reaction. Now take one example of addition reactions. Addition of butadiene plus ethene to give cyclohexene. And similarly, take another example. Propene adds to hydrogen in the presence of nickel to form propane. In both the examples, the number of atoms of the reactants are incorporated into the final product. So addition reactions are also examples of 100% atom economical reactions. Next, let us see substitution reactions. Atom economy is only 65.4%. For example, if you take a reaction of methylamine with ethyl propanoate, the product is N-methyl propionamide and ethyl alcohol. Ethyl alcohol is a byproduct, whereas N-methyl propionamide is the required product. When we look at the reactants formula weight and utilized atoms formula and formula weight, unutilized atoms formula and formula weight. The reactants The formula weight total is equal to C6H15NO2. Vasu, Vasu, oh Vasu.